It's important that you've watched a video on a trapped ion modeled by a mass in a spring harmonic oscillator. If you haven't watched that, then I'm going to refer to things that you might say that you don't know anything about. So do that first before you go through this stuff with me. And here's an interesting thing that I didn't understand at first, but why should we be worried about how much the ion is wiggling around? That we're not measuring the wiggle, we're measuring the energy states of that ion. Lower energy, or let's say lowest energy of the electronic ion state is 0. The next level up is a 1. And we try to keep the thing slowed down enough that it doesn't, let's say those are the only two allowed. So we have to be really cooled off and not disturbed. But I digress, like I normally do. So the wiggling around, if you only have one qubit, one ion, then the wiggling around doesn't make any difference. If you have more than one qubit and they're tied together or close proximity, then that makes a big difference. So that's really important. The wiggling around messes up the measurement. So we need to be aware of this, and we need to figure out ways to offset it or measure it or make allowances for it. From the harmonic oscillator one, we should know that the potential energy is this value. Now the potential energy related to X, so it changes as X gets farther away or closer. Farther away, the potential energy gets greater. This has to do with the frequency that it's oscillating, and this is the mass of the ion. And if you want me to show it with this thing, this is the potential energy. This is the X value, which as it gets greater, the potential energy gets greater. As this is the frequency of the oscillation of the thing, which changes the potential energy, and this is the mass of the ion. Moving along, the energy, we'll pretend like this H is an E, which stands for the total energy. This P squared over 2m is the traditional classical 1/2 mv squared for kinetic energy, and this is the potential energy. But in the quantum mechanical world, and this is where we're changing things a little bit, the Hamiltonian represents the energy, but it's an energy operator. It operates on something. It operates on the function. And here we see that example. The operator H operates on the function psi with respect to X. It's a function of X. And what we produce are discrete energy levels for that function. And we solve for the function using this relationship. We go from this to this. Now what changed? We had a momentum operator. It has a little hat on it, so it's an operator, squared over 2m. If we come down here, you'll see that that p squared is replaced by h bar squared, which is Planck's constant, so now we're in the quantum mechanical world, and the second derivative with respect to x. This comes up with a equation which is really complicated looking. So according to this text, we're going to do something which makes no sense when you first look at it. We're going to simplify the equation by introducing another variable. Now, how can you simplify if you introduce another variable? But this variable at least has things that we already know about. It's got mass, it's got omega, it's got the h value from Planck's constant. And it has, and the other side, we just used algebra to show that the x is also equal to this times the magical variable here. So if you look at this equation, this has all that stuff substituted in. But something weird happens. This function phi or phi, phi fum, and here's this dimensionless variable, and so we create a new function. So it's like we took that thing and totally switched it around. At first, it just seems like no sense at all. But the result of coming up with those changes does look a little simpler than what we had, because we've got this discrete energy value. And remember, this phi is phi of, is it phi of x? No, it's phi of this strange variable. So this is not a function of x. This all comes down into this form, which now it's looking a lot simpler, but we introduce another variable called the dimensionless energy. Isn't that scary or awesome? Anyway, we take it's the E divided by the things that we already know, h bar omega. This is something that I thought about trying to cover in here, and my decision said, forget it. Following that would get so mathematical that it would even turn me off, and I wouldn't even watch my own videos. So here's the results of all this. If we solve for that function, we will find that these epsilon n, which is the dimensionless energy, looks like this. And then when we take that, substitute back in with the real energies, here's what we get for the solutions. And notice the solution is not a continuous one. The solution is a series of energies separated by one another. And this series of energies is exactly what happens in the quantum mechanical world. You don't have continuous range of energies. You have discrete energies that are possible, and those in between just don't happen. Wave functions. It gets even worse here. We take the weird equation that we had up there, and we mix the things around. We've got a psi of x, and then we have all this other garbage, and we do have this e to the minus t squared over 2, which that piece definitely is a wave function. And it mentions something about Hermite polynomials, and it gets so mathematical that, like I said, my head's starting to hurt, and I'm even embarrassed to talk about it. And the wiggling of the ion is mentioned for completeness. So we'll kind of abandon this. We'll put it in the background. We'll understand that it's there, but we're going on now to the energy states. And that will be the next video, because I think you're probably worn out by now, and definitely I am worn out.